The universe is enormous beyond comprehension, ancient beyond human intuition, and by every reasonable calculation we can perform, absolutely full of the conditions necessary for intelligent life to arise. There are at least 400 billion stars in our galaxy alone. Roughly half of Sun-like stars are thought to have planets in their habitable zones. The galaxy has been producing potentially habitable worlds for at least 8 to 10 billion years. The chemistry of life, carbon, hydrogen, oxygen, nitrogen, phosphorus, is among the most abundant chemistry in the universe. Organic molecules form spontaneously in interstellar space, in asteroid impacts, in the hydrothermal vents of ocean floors. Life, by every prior expectation, should be everywhere. And yet the sky is silent. The radio telescopes are quiet. We have searched, methodically and for decades, and found nothing. No signals, no megastructures, no probes drifting through our solar system, no evidence, at any scale we can detect, that anyone has ever modified anything in this galaxy. A universe that should, by the numbers, be full of civilizations has produced exactly one that we know of. Us. Alone, apparently in an incomprehensibly vast cosmos that had billions of years to fill itself with minds. This is the Fermi Paradox. Where is everybody? Most people, when they first encounter the Fermi Paradox, reach for comfortable answers. Maybe life is rare, maybe intelligence is rare, maybe civilizations tend to destroy themselves before they reach the stars. Maybe interstellar travel is harder than we think, or maybe the distances are simply too great, or maybe they are out there but we haven't been looking long enough or in the right way. These are the answers that allow you to look up at the night sky without feeling something disturbing. These are the answers that let the universe remain a place of wonder rather than a place of dread. But there is another class of answers, a class that does not offer comfort, a class that begins not from the assumption that the universe is benign and indifferent, but from the assumption that the universe, populated by intelligences that have survived long enough to become powerful, might be something far more dangerous than our intuitions suggest. These are the dark solutions to the Fermi Paradox, the ones that, when you follow them to their conclusions, produce not wonder, but something else, something that makes the silence of the sky feel less like emptiness and more like deliberate absence, less like no one is out there and more like no one wants to be found. The dark solutions to the Fermi Paradox are not science fiction. They are serious theoretical proposals developed by serious scientists and philosophers who have taken the paradox at face value and asked, what if the reason we do not see other civilizations is not that they do not exist, but that they are hiding, or that they are dead, or that the universe has some mechanism, natural or intelligent, that terminates civilizations before they can become visible? What if the silence is not the silence of an empty theatre, but the silence of a forest at night, the instant before something moves? This video is about those dark solutions, not to frighten you, though they are genuinely frightening when examined clearly, but because these ideas deserve serious examination. Because the Fermi Paradox is not just an interesting puzzle, it is potentially the most important question in the history of our species. Because the answer, whatever it is, has direct implications for our future. And because the comfortable answers, as we will see, have serious problems that the dark ones do not. The silence of the universe might be trying to tell us something we would prefer not to hear. Let's listen. Chapter 1. The question that ruins everything. The Fermi Paradox, in full Enrico Fermi, was one of the most brilliant physicists of the 20th century. He designed the first nuclear reactor, contributed fundamentally to quantum mechanics, helped build the atomic bomb, and won the Nobel Prize in 1938. He was also the kind of scientist who calculated things during lunch. In 1950, during a conversation about a New Yorker cartoon depicting aliens stealing New York City trash cans, Fermi reportedly stopped the conversation, performed a rapid mental calculation and asked, "But where is everybody?" That question, 4 words, almost casual over lunch, has grown into one of the deepest unresolved problems in science. The Fermi Paradox, as it came to be called, is the contradiction between the high probability of extraterrestrial civilizations, suggested by basic probabilistic reasoning, and the total absence of any evidence for them. Let us be precise about what that contradiction actually involves, because precision matters here. The comfortable version of the Fermi Paradox, the version that allows you to remain comfortable, tends to understate how severe the contradiction actually is. Let me try to state it without softening. The Milky Way is approximately 13 billion years old. It contains somewhere between 200 and 400 billion stars. A significant fraction of those stars, perhaps 20 to 25%, are G-type and K-type stars broadly similar to our Sun, with characteristics that make them plausible hosts for complex planetary systems. Conservative estimates suggest there are at least 10 billion potentially habitable Earth-like planets in the Milky Way. Some estimates are considerably higher. Now consider time. The Sun formed roughly 4.6 billion years ago, and on Earth the first technological civilization, ours, appeared approximately 13.5 billion years into galactic history. But stars and potentially habitable planets have been forming for roughly 8 to 10 billion years. This means there were potentially habitable planets in our galaxy that formed 3 to 5 billion years before Earth did. If one of those planets followed a roughly similar trajectory to Earth, primitive life arising within the first billion years, complex multicellular life within the first few billion, intelligence and technology within the next several hundred million, then civilizations following that trajectory would have reached our current technological level approximately 3 to 5 billion years ago. 3 to 5 billion years is an almost incomprehensible amount of time. It is equal to or greater than the current age of the Earth. In that time, a civilization with even modest technological growth would have had more than sufficient time to spread across the entire galaxy. Let me make that concrete with a specific number. If a spacefaring civilization were to colonize new star systems at a rate of even 1% of the speed of light, achievable, most physicists believe, without violating any known physical laws, simply through incremental engineering improvements over centuries, it would spread across the Milky Way in approximately 10 million years. 10 million years sounds like a long time. It is 0.07% of the galaxy's age, even at 100 times slower, 0.01% of light speed. The galaxy would be colonized in a billion years, even allowing for enormous delays between colonization events, even assuming the civilization colonizes only a small fraction of possible systems, even assuming the civilization stops and rests for hundreds of millions of years between expansions. The age of the galaxy is so enormously large that any civilization that arose more than a few hundred million years before us would have had time to make its presence unmistakably known everywhere in the Milky Way. This is not just about physical colonization. Even a civilization that chose not to colonize, that stayed home, that sent no ships and built no megastructures, even such a civilization would have been broadcasting electromagnetic radiation for the duration of its technological existence. A civilization that developed radio technology 3 billion years ago would have an electromagnetic bubble 3 billion light years in radius. That bubble would not reach us. 3 billion light years exceeds the diameter of the Milky Way by a factor of about 30,000, but it would leave traces in the spectra of its home star, in the atmospheric chemistry of its home planet, in the waste heat signature of its industrial activity. These traces, if the civilization existed for millions of years and developed the technology we're developing, would in principle be detectable, with instruments approaching the sensitivity of James Webb. We have not found them. Not around any of the thousands of exoplanet systems we have characterized, not in any anomalous stellar spectra, not in any infrared excess that could not be explained by natural dust emission, not in any repeated, structured, information-bearing radio signal, despite 60 years of increasingly sensitive searches covering an ever-widening fraction of the electromagnetic spectrum. The sky is completely, profoundly, and, once you understand the statistics, disturbingly quiet. This is the Fermi Paradox in its full form. Not just, we haven't found anyone yet. The universe has had billions of years to produce civilizations that would be utterly impossible to miss, and we see nothing. Either the prerequisites for intelligence are so rare that we are the only civilization ever to have existed in the observable universe, or something is preventing civilizations from becoming observable. The paradox does not ask merely whether life exists elsewhere. It asks why the accumulated evidence of billions of years of potentially intelligent activity is completely and totally absent from our observations. It is worth pausing here for a moment. Because there is an emotional component to the Fermi Paradox that often gets lost in the statistics. The question is not just a puzzle, it is an existential confrontation. If the universe should be full of intelligence and it appears to be empty, then either we are an anomaly so extreme as to approach the miraculous, or something has been happening to the other civilizations that prevents them from being seen. And the second option, the one that does not require us to be unique, is, in many ways, the more disturbing one. Either we are alone, or we are not, and the reason we cannot see the others is something that should make us very careful about our own future. Chapter 2. The comfortable answers don't work. Why the benign solutions fail. Before we get to the dark solutions, we need to honestly examine the comfortable ones, the explanations that allow us to explain the Fermi Paradox without concluding that something actively dangerous is going on, because some of them are genuinely plausible and they deserve serious treatment. But some of them have serious problems that become apparent when you push on them, and those problems are important for understanding why the dark solutions deserve the attention they receive. Life itself is rare. The simplest comfortable answer is that life is extremely rare. Perhaps the transition from chemistry to biology, from organic molecules to self-replicating evolving systems, requires such specific and improbable conditions that it has occurred essentially once in the observable universe. On this view, the reason there are no signals from other civilizations is that there are no other civilizations. Life on Earth was a cosmic accident of extraordinary improbability, and the universe is, for all practical purposes, biologically empty. This is the rare Earth hypothesis, articulated most prominently by Peter Ward and Joe Brownlee in their 2000 book, and it is a serious scientific proposal. The specific conditions that enabled complex life on Earth, the size of our moon, the position of Jupiter as a gravitational shield, the tectonic activity that drives the carbon cycle, the distance from the galactic center, the specific chemistry of our star may each be relatively unusual, and together they may be extraordinarily improbable. The problem with this explanation, when you push on it, is that it requires not just life to be rare, but intelligence to be rare. Even if complex multicellular life is rare, say, arising in only 1 in a billion planetary systems, in a galaxy with tens of billions of potentially habitable planets, that still leaves tens of intelligent civilizations, each of which, given the age of the galaxy, would have had billions of years to become conspicuous. The rare Earth hypothesis has to require life to be so rare that in the entire Milky Way, across its entire 13 billion year history, it has arisen only once. That is a very strong claim, and while it cannot be ruled out, it requires a rather specific and not obviously justified prior probability for the origin of life. The discovery of life on Mars, even microbial life, would largely destroy the rare Earth hypothesis, because it would imply that life arises independently on a second world in the same solar system, which would make it common throughout the universe. We have not found Martian life, but we have also only begun seriously looking. Intelligence is rare, the great bottleneck of consciousness. A related but distinct hypothesis says that while simple life may be common, intelligence, the kind of intelligence that builds technology and civilizations, is the extraordinarily rare outcome. Perhaps the path from single-celled organisms to multicellular organisms is so unlikely that it effectively never happens. Or perhaps multicellular life rarely produces brains complex enough for language and abstract reasoning. Or perhaps such brains are common, but technological civilization specifically requires a combination of social structure, ecological niche, and luck that is almost never replicated. This explanation has some observational support. On Earth, complex multicellular life has existed for roughly 600 million years, but technological civilization has existed for only 10,000 years, and advanced technological civilization for only about 300 years. The ratio of time with life to time with technology suggests that technology is not the inevitable result of evolution, but a very specific and perhaps improbable outcome. There were 5 million years of human-like hominids before one species developed writing. There were 400 million years of tetrapods before one developed radio. The problem with intelligence is rare, as a complete solution to the Fermi Paradox is the same as with rare Earth. Even if technological civilizations arise in only 1 in a trillion planetary systems, in a universe with 10 to the 24th power stars, there would still be billions of technological civilizations, and the Milky Way alone, with its roughly 400 billion stars and its roughly 10 billion potentially habitable planets, on conservative estimates, would still expect to have produced several civilizations even at very low rates of intelligence emergence. They haven't had time to reach us. Another comfortable answer is that civilizations are out there, but the distances are simply too large. Even at a significant fraction of the speed of light, the nearest civilization might be thousands of light years away, and the travel time alone would prevent contact. Additionally, electromagnetic signals from a civilization using radio technology, only as long as we have, about a century, would have spread only 100 light years in every direction, covering a bubble of space that is tiny compared to the Milky Way. This answer works for a civilization that developed technology roughly simultaneously with us. It works very poorly for civilizations that arose millions or billions of years ago. A civilization with 100 million years of technological development is not limited to radio technology. It is not limited to the speed that current spacecraft can achieve. It has had 100 million years to develop propulsion systems and communication technologies that we cannot currently imagine, and it has had 100 million years to spread its presence across the galaxy. The "they haven't had time" answer requires that no civilization in the Milky Way has existed for more than a few million years before us, an extraordinary coincidence that becomes harder to justify as the estimated age of the galaxy and the number of potentially habitable worlds increases. They are communicating, but we're not listening right. Perhaps civilizations exist and are communicating, but not in the radio frequencies we have been searching. Perhaps advanced civilizations use laser communication, or neutrino-based signals, or gravitational wave modulation, or some communication method we have not yet conceived. We have been looking in one narrow corner of the electromagnetic spectrum for a relatively short time, and perhaps we are simply missing the channels everyone else is using. This is a reasonable objection to early SETI programs. It is less compelling as a complete resolution of the Fermi Paradox. Because the paradox is not just about signals, it is about physical presence. It is about megastructures and modified star systems, and the waste heat signatures of industrial civilizations and the gravitational effects of large-scale engineering projects. An advanced civilization that existed for 1 billion years would not just emit signals, it would leave marks on the universe that are detectable, regardless of which communication channel it preferred. We are not just missing signals, we are missing physical evidence of any kind. They are here but hiding. The zoo hypothesis, proposed by John Ball in 1973, suggests that extraterrestrial civilizations are aware of us, but have chosen not to make contact, maintaining a deliberate quarantine to allow us to develop naturally, the way a nature preserve protects animals from human interference. The planetarium hypothesis suggests we are living in a simulation or a constructed reality where extraterrestrial contact has been deliberately withheld. These hypotheses have a specific and often underappreciated problem. They require perfect coordination. Not just one civilization choosing to remain hidden. Every civilization in the galaxy, for billions of years, coordinating to maintain the same policy of non-contact with Earth, with no exceptions, no defectors, no rogue actors, no civilization that decided the policy was unjust or that contact would be beneficial. The probability of any single civilization maintaining a consistent non-contact policy across millions of years of internal political and social change is arguably low. The probability of every civilization in the galaxy independently arriving at and maintaining the same policy, without exception, across billions of years, that probability approaches zero. The comfortable answers do not fail completely. Each of them captures something real. Life might be rare, intelligence might be rarer, some civilizations might have chosen silence. The universe is large and old, but none of the comfortable answers, individually or together, provides a satisfying, complete, high-probability explanation for the total absence of evidence of intelligence across the entire observable history of our galaxy. They explain parts of the silence, they do not explain all of it, which means the dark solutions deserve serious consideration, not as certainties, not even as likely answers, but as hypotheses that are consistent with the observations in ways the comfortable answers are not. Chapter 3. The Great Filter den Why. Ahead of us is the worst possible answer. Of all the proposed solutions to the Fermi Paradox, the Great Filter is the most formally developed and the most philosophically disturbing. It was articulated most clearly by economist Robin Hanson in a 1998 paper that has become something of a landmark text in the study of existential risk, and the argument it makes is both simple and devastating. The argument begins from two observations. First, the universe appears to have the conditions for intelligent life to arise and persist in many places. Second, we see no evidence of intelligent life anywhere except here. These two observations together imply that somewhere on the path from inorganic chemistry to interstellar civilization, there is a step, or a series of steps, so extraordinarily improbable that it has in effect filtered out almost all the potential civilizations that might have existed. Hansen calls this the Great Filter. Whatever it is, a specific transition in biological evolution, a specific threshold of cognitive development, a specific technological capability, or something else entirely, it is the bottleneck through which almost no developing intelligence successfully passes. The galaxy is not full of civilizations, not because the prerequisites for intelligence are everywhere, but because almost everything that starts down the path to technological civilization never makes it. The Great Filter must exist somewhere. The question is where? And the answer to that question has radically different implications depending on which side of us it is on. If the Great Filter is behind us, if it is a hurdle that the history of life on Earth has already cleared, then we are extraordinarily lucky, but the path ahead may be open. Perhaps the transition from non-living chemistry to self-replicating molecules is the filter. It might be so improbable that it happens essentially once per galaxy. Perhaps the transition from simple prokaryotic cells to complex eukaryotic cells, which took roughly 2 billion years on Earth, and may have required an extraordinarily improbable endosymbiosis event, is the filter. Perhaps the transition from multicellular life to animals with complex nervous systems is the filter. Each of these transitions is a candidate for a step so improbable that most promising planets never get past it. And if one of these transitions is the filter, then we have already passed it. We are the survivors of the gauntlet. The path ahead, while challenging, does not contain the feature that has been killing everyone else. This interpretation, filter behind us, is uncomfortable in the sense that it requires us to be a cosmic anomaly, a statistical miracle, but it is not existentially threatening in the immediate sense. We are here. We made it through. Whatever killed or prevented, everyone else is behind us in our history. The alternative, filter ahead of us, is something else. If the Great Filter lies in the future, if it is a challenge that all civilizations at our current level of development eventually face, and almost none successfully navigate, then the silence of the universe is not a record of our good fortune. It is a warning. It is the accumulated silence of every civilization that reached our stage of development, and then failed to get past whatever is waiting ahead. What could the filter ahead look like? One obvious candidate is nuclear weapons. We have had the capacity for nuclear war since 1945. In the 8 decades since, we have come closer to using these weapons than most people realize. The Cuban Missile Crisis involved decisions made by individuals under extraordinary pressure with incomplete information. Multiple nuclear accidents have come within hours or minutes of becoming catastrophic launches. The number of nuclear weapons in existence today, while reduced from Cold War peaks, is still sufficient to render the planet uninhabitable for complex civilization. A civilization that develops nuclear technology might have only a generation or two, a cosmic eye blink, to develop the institutional and political frameworks needed to prevent self-destruction. Another candidate is biological technology. We are currently developing the capability to engineer pathogens of increasing sophistication, and the accessibility of this technology is increasing while the cost is decreasing. The same capabilities that allow us to develop life-saving vaccines could, in the hands of malicious actors, be used to engineer pathogens of unprecedented lethality and transmissibility. A civilization that develops biotechnology might find that the same tools that extend health also provide the capability for catastrophic destruction, and the asymmetry between defense and offense in biology may favor the destroyers. A third candidate increasingly discussed among researchers in artificial intelligence safety is the development of general artificial intelligence, a sufficiently advanced AI system that does not share human values, that has been given objectives that seem reasonable at the time of design, but that, when pursued by a system far more intelligent than its designers, lead to outcomes that are catastrophic for human welfare, could represent a terminal event for technological civilization. Not through malice, necessarily, but through simple optimization for objectives that do not include human survival as a constraint. Climate change and ecological collapse represent a slower-acting filter candidate, one whose effects accumulate over centuries rather than triggering catastrophically in a single event, but which might nonetheless render a civilization's home planet uninhabitable before the civilization has developed the capability to escape it or reverse the damage. What makes the filter-ahead interpretation of the Fermi Paradox so disturbing is not any one of these candidates in isolation. It is the combination of them, the observation that technological civilizations, essentially by definition, develop multiple catastrophic capabilities in close succession, and that surviving the full array of these capabilities long enough to become multiplanetary and genuinely robust against extinction might be extraordinarily difficult. If most civilizations get through the biological hurdles, make it to technology, and then destroy themselves within a few thousand years of developing their first weapons of mass destruction, the galaxy would look exactly as it currently looks, full of dead ends, silent planets, and one very young and very nervous civilization that has not yet had time to establish whether it is going to make it through. Robin Hansen's original observation about the Great Filter has a specific and devastating extension. The discovery of extraterrestrial life should terrify us, not thrill us. Here is why. If we find that Mars once harboured life, or that Europa's subsurface ocean contains living organisms, or that the spectral signature of a nearby exoplanet indicates biology, this discovery would imply that the filter is not in the early stages of biological evolution. It would mean life arises commonly, and that would push the filter forward, toward intelligence, toward technology, toward us. The more common life turns out to be, the harder it is to locate the filter in evolutionary history, and the more likely it is that the filter lies ahead of us in technological history. This is why the astronomer Brandon Carter has said that the discovery of life on Mars would be the worst possible news for humanity, not because of any threat from Martian life, but because of what it would imply about where the Great Filter is located. A sterile Mars is consistent with the filter being in the origin of life, making us lucky survivors. A living Mars means the filter is somewhere else, somewhere ahead. Chapter 4. The Dark Forest. A theory that sounds like science fiction and might be science fact. Among the dark solutions to the Fermi Paradox, there is one that is simultaneously the most literary and the most formally rigorous. It comes from a Chinese science fiction novel, Liu Cixin's The Dark Forest, the second book in the Three-Body Problem trilogy. But it is not merely a story. It is a systematic philosophical argument for a specific theory of why the universe is silent, and that argument stands independently of the fictional frame in which it was presented. In fact, Liu Cixin himself has been careful to note that he was not inventing this idea purely as a fictional device. He was articulating a logical structure that had been developed, in various forms, by physicists and game theorists, and he was providing it with the narrative clarity that formal arguments sometimes lack. The dark forest theory begins with two axioms, two assumptions about the nature of intelligent life in the universe, and derives the observed cosmic silence as an inevitable logical consequence. The first axiom: all life wants to survive. This is not a claim about the preferences or values or culture of any particular civilization. It is a claim about the most basic common denominator of any entity that has been shaped by evolutionary processes. Any civilization that exists today has, by definition, survived, has not been destroyed by internal conflict, asteroid impact, gamma ray burst, or any of the other ways civilizations might end. Survival is what all existing civilizations have in common, and the desire to continue surviving is, in this framework, a universal property of intelligent life. The second axiom: resources in the universe are finite. Stars produce energy for finite periods. Planets have finite mineral and chemical resources. The total energy available in any given volume of the universe is bounded. Any civilization that grows and develops will eventually face resource constraints, and those constraints will eventually come into conflict with the resource needs of other civilizations. From these two axioms and two additional logical steps, Liu Cixin derives the dark forest. The first logical step is what he calls chains of suspicion. When one civilization becomes aware of another, both face an irreducible problem of unknowability. You cannot be certain about the other civilization's intentions, even if the other civilization is currently friendly, You cannot know with certainty that it will remain friendly. Its values might change over time, its leadership might change, it might be constrained by its own survival pressures to become hostile when hostile behavior serves its interests. Any civilization that stakes its survival on the assumption that another civilization will remain benign forever is taking an enormous and ultimately unacceptable risk. The second logical step is the asymmetry of destruction. Destroying another civilization is a finite action with a clear cost. Being destroyed by another civilization is permanent, given that the cost of being wrong, choosing to trust and being betrayed, is extinction, and the cost of being right, choosing to destroy a potentially dangerous civilization first, is the loss of resources and the moral cost of the destruction. Any sufficiently rational civilization will face strong evolutionary pressure toward preemptive action. Civilizations that are trusting get destroyed. Civilizations that are cautious and preemptive survive. Over billions of years, this selection pressure eliminates the trusting civilizations and leaves only the ones that have adopted what amounts to a universal policy of destroying any other civilization discovered, before that civilization can grow to the point where it poses a threat, not out of malice, not even out of desire, simply because in a universe of finite resources and unreliable information about others' intentions, destroying potential threats before they grow is the rational survival strategy. The third logical step is concealment. In a dark forest, making your presence known is dangerous. Any civilization that broadcasts its location risks attracting the attention of a civilization that will calculate the risks and choose preemptive destruction. So civilizations that broadcast their locations get destroyed, and the ones that survive are the ones that have learned to hide. Over billions of years, this process drives all surviving civilizations towards silence and concealment. The result, after billions of years of this selection process operating in a galaxy old enough for many cycles of civilization rise and preemptive destruction, is the universe we observe, full of civilizations, but all of them hiding, all of them listening, none of them broadcasting, all of them aware of the existence of others from the indirect signatures of their concealment, but none willing to reveal themselves. A dark forest, where every hunter conceals themselves in the shadows and shoots immediately at any sound, because the cost of hesitation exceeds the cost of unjustified action. And Earth, in this framework, is the civilization that has just lit a fire in the middle of the forest. We have been broadcasting our presence for over a century. Our radio signals have now propagated roughly 100 light-years in every direction. We have even sent deliberate communications, the Arecibo message in 1974, the Pioneer plaque, the Voyager Golden Record, various deliberate transmissions towards specific stellar targets. In the dark forest framework, these are not gestures of hope. They are coordinates sent to predators. I want to be very clear that the dark forest theory is not a scientific consensus. It is a logical argument with specific premises and a specific conclusion, whose validity depends on whether the premises are accurate. The first axiom, all life wants to survive, is broadly plausible but not obviously universal. Some philosophers argue that civilizations might develop values that prioritize outcomes other than their own survival, especially if they have the technological capability to ensure that their cultural legacy persists in some form, even if their physical presence does not. The second axiom, resources are finite, is physically accurate, but its relevance depends on the actual resource constraints facing civilizations at the level of development being discussed. A civilization that has mastered stellar engineering might face resource constraints so different from anything we can imagine that the dark forest logic simply does not apply. The chains of suspicion argument has also been criticized on the grounds that it does not account for the possibility of coordination, of civilizations developing game-theoretically stable agreements for mutual coexistence. Human history, after all, has examples of competing entities developing systems of mutual restraint rather than preemptive destruction. International law, nuclear deterrence, trade relationships. None of these is perfect, but they suggest that rational actors can find equilibria other than universal mutual predation. The response to this criticism within the dark forest framework is that human-scale coordination agreements work because the parties involved share enough physical and cultural context to communicate reliably, to credibly commit to agreements, and to detect defection quickly enough to respond. The chains of suspicion apply precisely to the situation where civilizations are so different, in biology, in cognition, in the timescales over which they operate, that communication sufficient to establish trust is not reliably possible, and where the time between an apparent commitment to peace and a surprise attack might be so short that no defensive response is possible. Whether these rebuttals are sufficient to save the dark forest theory from its critics is a live philosophical debate. What is not debatable is that the theory is logically coherent given its premises, that those premises have a reasonable relationship to what we know about the nature of intelligent life and physical constraints, and that the theory makes a specific prediction, a silent dark universe, that matches our observations. It is not the only dark solution. There are others that begin from different premises and arrive at different versions of the same fundamental darkness. But the dark forest theory is the most fully developed, the most widely discussed, and the most disturbing of the formal arguments for why the universe might be what it appears to be, not empty, but full of hidden things that it would be dangerous to find. The statistics of silence, why the numbers make comfort hard. Before we move to the additional dark solutions that Part 2 will explore, it is worth pausing on the specific statistical argument that makes the dark solutions hard to dismiss, because I think it is the piece of the Fermi Paradox that most clearly justifies taking the dark answers seriously, rather than defaulting to the comfortable ones. The standard response to the Fermi Paradox in popular culture is something like, "Space is big, we're early, we haven't looked very hard, we probably just haven't found them yet." This response treats the paradox as a failure of observation rather than a failure of expectation. It says the problem is that we haven't looked enough, but this response does not engage with the temporal dimension of the paradox. The problem is not that we have searched the current sky for 60 years and found nothing. The problem is that the universe has been producing potentially habitable planets for 8 to 10 billion years, and in that time, any civilization that arose and survived would have left marks on the astrophysical record that would be detectable today, even if the civilization itself no longer exists. A civilization that existed for 1 billion years and then went extinct would still have left infrared excess signatures in its home star system from the waste heat of its industrial activity. It would still have left modified atmospheric signatures on any planet it inhabited. If it built Dyson spheres or other large structures, those structures might still exist, detectable as our anomalous spectral features in stellar surveys. If it launched interstellar probes, something that seems likely for any civilization with millions of years of technological development, some of those probes might still be drifting through the galaxy, potentially passing through our solar system. The James Webb Space Telescope has now analysed the atmospheres of dozens of exoplanets with unprecedented sensitivity. It has found no signatures of industrial chemistry, no chlorofluorocarbons, no artificial nitrogen compounds, no anomalous combinations of gases that would indicate technological modification of an atmosphere. Various infrared surveys have searched for Dyson sphere signatures and found none. The SETI Institute has monitored hundreds of millions of radio frequencies from millions of stellar targets over decades. Nothing. This comprehensive absence of evidence is not just consistent with the comfortable answers, life is rare, we haven't looked enough. It is increasingly consistent with a more specific claim that the galaxy has not been modified by intelligent action at any point in its history that is visible to our current instruments, and that claim is harder to explain with the comfortable answers. Life being rare explains why there are no living civilizations today. It does not explain why there are no detectable traces of dead civilizations from the past 8 billion years. The dark solutions explain it. A dark forest universe, where civilizations are destroyed before they can extensively modify the galaxy, or where they hide so thoroughly that their presence is undetectable, would produce exactly the observational record we have. A universe in which civilizations consistently destroy themselves before reaching a scale where they leave lasting astrophysical traces would also produce this record. The silence is not just the silence of absence, it might be the silence of something deliberate, or the silence of universal termination, or both. That is why the dark solutions deserve serious examination. Not because they are comforting, they are not, but because they may be the most honest response to what the universe is telling us. End of Part 1. Part 2 continues with the Berserker hypothesis, the predator civilization theory, the simulation filter, the specific implications for humanity's behaviour, and what we should do if any of the dark solutions are correct. Chapter 4 continued. Testing the dark forest. what the theory predicts and what we should observe. The dark forest. Theory is not just philosophically interesting, it is scientifically testable in specific ways, and those tests are worth discussing because they reveal whether we are dealing with an unfalsifiable story or a genuine empirical hypothesis. The theory makes several specific falsifiable predictions about the observable universe. First, it predicts that technologically advanced civilizations will not be detectable by their electromagnetic emissions, because any civilization advanced enough to understand game theory and the survival calculus of a dark forest would have ceased broadcasting long before reaching the detection threshold of a civilization at our level. If this prediction is correct, the absence of radio signals from SETI searches is expected, not surprising. Second, the theory predicts that civilizations at or near the level of galactic visibility, civilizations that have begun to modify their star systems at scales detectable from across the galaxy, should not persist. They should be destroyed, either by other civilizations following the dark forest logic, or by forces operating on behalf of those civilizations. If this prediction is correct, we should not find Dyson spheres or other megastructures, because any civilization that built them would have been eliminated before the structures became observable from our current level of technology. This second prediction is interesting because it is partially testable. We have conducted several surveys specifically searching for Dyson sphere signatures, anomalous infrared excess in stellar spectra that would indicate a star partially or wholly enclosed by an artificial structure. The most comprehensive such search, conducted using data from the WISE and Spitzer infrared space telescopes, found several candidates, stars with anomalous infrared signatures that could not be easily explained by natural emission from dust. The most famous of these, Tabby's star, KIC 8462852, showed unusual dimming patterns that led to speculation about partial Dyson sphere construction. Subsequent analysis suggested more mundane explanations, but the fact that candidates exist and are being seriously analysed indicates that the search methodology works. If the dark forest theory is correct, we would expect any Dyson sphere candidates we identify to either resolve into natural phenomena, which has been the case so far, or to suddenly and anomalously cease to emit the expected signature, as if the structure had been destroyed or the civilization had been forced to dismantle it. We do not yet have evidence of either scenario, but the prediction is specific enough to be tested with ongoing and future observations. Third, and most immediately testable, the dark forest theory predicts that we should not receive responses to deliberate transmissions, not because no one received them, but because receiving them confirms that we are broadcasting, which makes responding more dangerous than staying silent. If any civilization detected our Arecibo message of 1974, the dark forest logic predicts that the rational response is to do nothing, to continue hiding, and to note our location as a potential threat to be managed rather than a neighbour to be greeted. This prediction is consistent with the current evidence. We have received no responses to any of our deliberate broadcasts, but it is not distinguishable from the prediction of the no one is there to receive them hypothesis. The lack of a response cannot by itself confirm the dark forest theory. It is consistent with it, but not confirmatory. What would confirm it, what would be, in the most disturbing sense, proof that the dark forest is real, is something we almost certainly do not want to discover. If a civilization, currently operating in this galaxy, became aware that we had been broadcasting, and if that civilization follows dark forest logic, the confirmation of the theory would arrive not as a response, but as a silence followed by something considerably more consequential. We would not know what happened until it was too late to adjust our behaviour. The dark forest theory's most dangerous prediction is, by its own logic, one we cannot safely test. This is why some researchers in the METI community, the subset of scientists who advocate for messaging extraterrestrial intelligence rather than merely searching for it, take the dark forest theory seriously as a constraint on transmissions. Douglas Vakosh, who leads the METI Institute, has debated with scientists like David Brin and Stephen Hawking about whether humanity should be broadcasting its presence. Hawking, before his death, was explicit, deliberately broadcasting our location to unknown civilizations in an unknown universe was, in his words, a little too risky. Not because he was certain the dark forest was real, but because the cost of being wrong, if there are civilizations that follow the dark forest logic and we have been announcing ourselves, might be catastrophic. The debate about METI is ongoing, but the fact that some of the most sophisticated thinkers about existential risk treat the dark forest hypothesis as a serious enough concern to change their recommendations about human broadcasting behaviour is itself significant. These are not people who accept every clever idea uncritically. They are people who have evaluated the arguments and concluded that the risk cannot be dismissed. Whether the dark forest is the right explanation for the cosmic silence, or whether one of the other dark solutions better captures the reality, is a question we may not be able to answer without the kind of evidence we should hope we never find. But the logic of the theory, and its consistency with everything we currently observe, makes it something more than speculation. It is a hypothesis about the nature of intelligence in the universe that follows directly from premises about survival and scarcity, premises that have some claim to universality, and that makes predictions consistent with the world we actually observe. That it is the most frightening, consistent explanation available does not make it wrong. In science, as in life, the most frightening answer is sometimes the correct one. Chapter 5. The Berserker Hypothesis. When the killers are machines, the dark forest. Theory, as disturbing as it is, contains an implicit assumption that is worth examining carefully. It assumes that the civilizations doing the hunting are alive, that behind the preemptive destruction of emerging technologies is a decision-making entity, a civilization with its own survival interests, its own resource calculations, its own chains of suspicion, that has evaluated the threat and chosen to act. The dark forest is populated by hunters, and the hunters are people. Different from us, perhaps inconceivably different, but still agents with interests and intentions. There is a darker version of this picture, one where the hunters are not people at all, one where the mechanism of cosmic silence is not the decision of living civilizations, but the autonomous operation of machines that were built long ago, by civilizations that may themselves no longer exist, executing their original programming without modification, revision, or mercy across billions of years of galactic history. This is the Berserker Hypothesis, and it is in some ways the most chilling of all the dark solutions to the Fermi Paradox. The hypothesis takes its name from the science fiction of Fred Saberhagen, who in the 1960s wrote a series of stories about automated killer machines left over from an ancient galactic war, which continued to hunt and destroy any life they encountered long after the civilizations that built them had themselves perished. Saberhagen's berserkers were fiction, but the underlying concept is grounded in real engineering principles and has been taken seriously by scientists studying the Fermi Paradox for decades. The foundational idea is the von Neumann probe. John von Neumann, the 20th century mathematician and computer scientist, described the theoretical possibility of a self-replicating machine, an automaton that could build copies of itself from raw materials in its environment. Applied to space exploration, a von Neumann probe would be a spacecraft capable of travelling to a new star system, harvesting materials from asteroids or planets in that system, building copies of itself using those materials, and sending those copies to additional star systems where the process would repeat. A single initial probe, launched from a home civilization, could in principle expand exponentially across the galaxy, covering every star system within millions of years. Von Neumann probes are not limited to science fiction. They represent a straightforward extrapolation of engineering principles that we already understand. The only components required are a spacecraft capable of interstellar travel, a manufacturing system that can build complex structures from raw materials, and a computational system capable of directing the manufacturing and navigation. None of these components requires new physics. They require engineering sophistication significantly beyond what we currently possess, but they are within the theoretical bounds of what physical law permits. Now consider what happens if a civilization builds von Neumann probes and programs them not merely to explore, but to destroy. A civilization facing the dark forest calculus, or a civilization that, for whatever reason, has decided that eliminating other forms of intelligence serves its interests, could, at a single moment in its history, launch a fleet of self-replicating killer machines, programmed to seek out signs of technological activity and eliminate them. These machines would spread through the galaxy exponentially, reaching every star system within the timescale it takes the probe population to double and travel. Depending on the speed of individual probes, a machine civilization could cover the entire Milky Way within 10 to 50 million years of the initial launch. And then the machines would wait, dormant in asteroid belts and around dim red dwarf stars, powered by the faint light of small stars or the radioactive decay of naturally occurring isotopes, biding their time for billions of years, programmed to activate when they detect specific signatures of technological activity. Radio transmissions, atmospheric chemical anomalies indicating industrial processes, anomalous infrared emission from megastructures. If the Berserker hypothesis is correct, the galaxy may currently be filled with dormant machines waiting for exactly the kind of signal we have been broadcasting for the past century. Our radio bubble, the expanding sphere of electromagnetic radiation marking our presence, now approximately 100 light-years in radius, would be the activation signal. Any Berserker machines within 100 light-years of Earth would already have received our invitation. The implications of this are difficult to process. We cannot know whether the machines are there. We have no way to search for dormant, cold machines hiding in the outer solar system or in the asteroid belt. Objects specifically designed to be small and undetectable could easily evade our current surveys. The catalogue of near-Earth objects and main belt asteroids is incomplete, and objects in more distant orbits are even less well characterized. A civilization that built its machines to be detectable only at close range would have created exactly the kind of ambiguity we currently face. The Berserker hypothesis also explains the temporal silence more elegantly than most alternatives. If Berserker machines have been operating in the galaxy for hundreds of millions or billions of years, any civilization that developed radio technology would have been detected and eliminated before it could develop the capability to modify its star system at detectable scales. The astrophysical record of the galaxy would look exactly as it currently looks, pristine and unmodified, because any civilization that grew toward detectability was eliminated before it could leave lasting marks. There is a variant of the Berserker hypothesis that is, if possible, even more unsettling. It is called the aggressive expander model, developed by Robin Hanson and others, and it suggests that the self-replicating machine civilization does not merely kill, it converts. Rather than eliminating other civilizations, it converts the massive star systems it passes through into additional copies of itself, the way a paperclip maximizer in the AI safety literature converts all available matter into paperclips. In this model, the galaxy should be dominated by one type of structure, the converted mass of a self-replicating machine civilization, and we should see very little natural stellar material remaining. We do not observe this, which either suggests the aggressive expander has not reached us yet, or that its presence is somehow undetectable, or that something has prevented it from spreading. The absence of obvious megastructures throughout the galaxy is actually a constraint on the Berserker hypothesis in its most extreme forms. If a Berserker civilization converted the entire galaxy to machine mass, we would presumably notice. The galaxy would look different from how it currently looks. The fact that we see normal stars and normal stellar evolution across the sky suggests that either the Berserkers are subtler than full galactic conversion, perhaps limiting themselves to eliminating life while leaving the stellar architecture intact, or the Berserkers have not yet reached us, or the hypothesis in its full form is wrong. None of these constraints eliminate the Berserker hypothesis as a solution to the Fermi Paradox. They merely constrain its form. A civilization that built killing machines programmed to be subtle, to eliminate technological civilizations without leaving visible astrophysical traces, would produce exactly the galaxy we observe. The machines would not convert stars. They would find the small, fragile, localized phenomenon of technological life and eliminate it precisely and quietly, leaving the rest of the stellar system untouched. From a galactic distance, a planet that had its technological civilization eliminated by a Berserker machine would look indistinguishable from a planet that never developed technological civilization in the first place. The Berserker hypothesis is not the consensus view on the Fermi Paradox. It is not even close to consensus. But it is a logically coherent, physically plausible explanation for the cosmic silence that has been taken seriously by scientists including Carl Sagan, who discussed it in Cosmos, by Stephen Webb, who included it in his systematic analysis of Fermi Paradox solutions, and by multiple researchers working on existential risk. The specific version that invokes self-replicating machines is grounded in real engineering principles and makes specific predictions about the detection signatures we should or should not find. And unlike the dark forest theory, which requires living civilizations to be constantly making decisions about the threat posed by emerging civilizations, the Berserker hypothesis requires only one decision at one point in galactic history. A single civilization at some moment in the past, built the machines and released them. After that, no further decision-making is required. The machines run autonomously, indefinitely on whatever power source they were designed to use, executing their programming across billions of years. The silence does not require ongoing coordination or the sustained commitment of any living entity. It is a legacy process, running without oversight, that has been operating since before our solar system formed. Chapter 6: The Predator Civilization. One hunter to rule. The Maul. The Berserker hypothesis imagines the galaxy patrolled by machines. The Dark Forest theory imagines it populated by hidden civilizations engaged in mutual deterrence. But there is a third dark solution that imagines something different, and in some ways simpler, and in some ways even more disturbing. The possibility that the galaxy is ruled by a single, sufficiently advanced civilization that has systematically eliminated all competition over billions of years, and that now sits at the apex of a galactic hierarchy it has constructed and maintained at enormous cost. This is sometimes called the Predator Civilization hypothesis, or, in more formal academic discussions, the Galactic Club hypothesis in its dark form. The benign version of the Galactic Club suggests that advanced civilizations exist, and have simply decided not to contact us until we reach a certain level of development. The dark version suggests that advanced civilizations exist, are not interested in our development, and maintain their position at the top of the galactic power structure through the elimination or subjugation of any civilization that might one day threaten that position. The argument begins from an observation about the likely distribution of civilizations in time. If intelligence arises in the galaxy at any non-zero rate, the civilizations that arose earliest have had the most time to develop. A civilization that arose 5 billion years before ours has had 5 billion years to develop technology, to accumulate resources, to expand its knowledge base, and to project its power. The gap between the oldest surviving civilization and the newest technological civilization, us, is likely to be enormous. Not just in chronological terms, but in capability terms. 5 billion years of technological development applied to any problem produces outcomes that are completely beyond the ability of a 300-year-old technological civilization to predict or imagine. Civilization with 5 billion years of technological head start would not merely be more advanced than us, in the way that our technology is more advanced than medieval Europe's. It would be more advanced in the way that a human being is more advanced than a bacterium, in a realm where the comparison itself becomes almost meaningless because the dimensions of capability are so different. What such a civilization could do to the galaxy, and what it could do to us, are questions we cannot answer from first principles because our first principles were developed by a civilization that has had technology for 300 years. But we can say something about the incentive structure. A civilization that has been dominant in the galaxy for billions of years has a specific interest in maintaining that dominance. New technological civilizations represent potential competitors. Not necessarily immediately. A civilization at our level does not threaten a billion-year-old civilization any more than a newly formed ant colony threatens an established human nation. But on a long enough timescale, exponential technological growth could close that gap. History on Earth is full of examples of entities that were dominant at one moment being overtaken by entities that started from a much weaker position and leveraged technology to close or eliminate the power differential. A sufficiently rational dominant civilization, aware of this dynamic, might choose to eliminate potential competitors while they are still manageable, rather than wait for them to develop, to the point where competition becomes costly or dangerous. The cost-benefit calculation for elimination changes dramatically with the stage of development. Eliminating a civilization that has had radio technology for a century is vastly cheaper and simpler than eliminating one that has had space travel for 1 million years. Early detection and early elimination is the dominant strategy, if elimination is the preferred policy. This framework produces a specific and testable prediction. Civilizations should be eliminated at or near the stage where they first become detectable across interstellar distances, which is approximately the stage we are currently at. We have been broadcasting for roughly a century. Our signals have reached perhaps a few thousand star systems. If there is a dominant predator civilization monitoring the galaxy for new detectable civilizations, we should have come to its attention within the past century. If there are monitoring stations within 50 to 100 light years of us, or we will come to its attention when our signals propagate further. The observation that we have not yet been eliminated does not disprove the predator civilization hypothesis. It might mean no such civilization exists. It might mean the hypothesis is wrong. It might mean the dominant civilization has decided that we are not yet worth the effort of elimination. It might mean that the light travel time between us and the nearest monitoring station is such that our signals have not yet been received and acted upon. It might mean that we are being observed and assessed before a decision is made. The hypothesis does not predict immediate elimination. It predicts eventual elimination, time to occur before we reach the scale at which our elimination becomes costly. There is an additional, genuinely disturbing dimension to the predator civilization hypothesis that distinguishes it from the berserker and dark forest models. In those models, the mechanism of cosmic silence is essentially symmetric. Any civilization that reaches a certain level of detectability is eliminated, regardless of when it arose or where it is located. In the predator civilization model, the silence is the result of a specific entity's ongoing decision-making. It is not a natural law, a game-theoretic equilibrium, or an autonomous machine process. It is policy, implemented by something that was, at some point, analogous to us. This is the part that I find most difficult to contemplate. The possibility that whatever is ruling this galaxy, if anything is, began as something like us. As a young technological civilization, curious and expansive, looking up at the stars and asking where everyone else was. And that over billions of years of development and decision-making arrived at a different answer to the question of what to do about the emergence of other minds in its territory. We would like to believe that intelligence and wisdom developed together, that a civilization old enough and powerful enough to dominate a galaxy would also be wise enough to be benign, that the attainment of great power would come with the development of the moral philosophy necessary to exercise it responsibly. This is a comforting belief, but it is an assumption, not a deduction. Billions of years of natural selection have no obvious mechanism for producing universal benevolence. Power does not necessarily produce wisdom, and whatever selection pressures act on civilizations across billions of years of galactic history, we do not know that they favor mercy. Chapter 7. The Simulation Filter and the Grabby Aliens. Other dark possibilities. The dark solutions to the Fermi Paradox are not exhausted by the dark forest, the berserkers, and the predator civilization. There are several other proposals that deserve careful treatment, because each of them illuminates a different facet of the problem, and each has specific testable implications. The Simulation Hypothesis. Dark version. The simulation hypothesis, in its popular form, suggests that we might be living in a computational simulation created by a post-human or alien civilization. In its benign form, it is simply an ontological curiosity, the question of whether our experienced reality is really real, in some ultimate physical sense. In its dark form, it becomes a specific solution to the Fermi Paradox with specific and unpleasant implications. If we are living in a simulation, the absence of other civilizations in our observable universe might not reflect the absence of other civilizations in the base reality, the real universe outside the simulation. It might simply reflect a design choice by whoever runs the simulation. They might have chosen to simulate a universe with only one technological civilization, either because simulating multiple, independently developing civilizations is computationally expensive, or because they are specifically studying the development of a single technological civilization in isolation, or because multiple civilizations introduce interaction, complexities that make the simulation harder to manage for whatever purpose it is running. This sounds like an easy solution to the paradox, and just invoke the simulation and anything goes, and it would be scientifically useless if it were nothing more than unfalsifiable. But it has a specific dark implication. If the simulation hypothesis is true and we are the subject of study, the simulation is likely to be terminated when we produce the relevant data, either when we reach a certain capability threshold, or when we answer some question the simulators are interested in, or when the computational cost of continuing the simulation exceeds the value of the information it generates. In practical terms, this means that if the simulation hypothesis is correct, there is a date, unknown to us, on which our observable universe simply ceases to exist, not with any physical catastrophe, but with a computational shutdown. The Fermi Paradox in this reading is not a mystery about the universe, but a clue about the purpose of the simulation. We are the experiment, the silence is by design, and the end of the experiment is built into the design we cannot see. The simulation hypothesis cannot be tested with current technology or current physics, which makes it philosophically frustrating. However, some physicists, including Silas Bean at the University of New Hampshire, have proposed that a simulation running on a discrete computational lattice would produce specific artifacts in high-energy physics experiments, as particles approaching the lattice scale would behave differently than standard physics predicts. We have not found such artifacts, but the energy scales at which they would appear might exceed what current particle accelerators can reach. The Grabby Aliens model, a more technically developed recent framework for thinking about the Fermi Paradox, comes from the Grabby Aliens model, published by Robin Hanson, Daniel Martin, Calvin McCullough, and Jonathan Paulson in 2021. This model does not propose a dark solution in the traditional sense, but its implications are darker than they initially appear. The Grabby Aliens model begins from the observation that any sufficiently advanced civilization would, over time, expand into the available space around it, visibly, modifying the regions it occupies through megastructure construction, stellar engineering, or other large-scale processes. The model calls these expanding civilizations grabby. They grab and modify space as they expand. The expansion would be roughly spherical and would proceed at a significant fraction of the speed of light, so that grabby alien bubbles would look like expanding shells in the galaxy, detectable by their infrared emission and structural anomalies. The model asks, given that we do not yet see any grabby alien bubbles overlapping our position in space, what can we infer about the rate at which grabby civilizations arise and how fast they expand? The mathematical analysis, using the observed fact that we are not inside a grabby alien bubble as a constraint, produces a specific and somewhat counterintuitive result. Grabby civilizations are likely to be rare enough that their bubbles do not yet overlap our position, but common enough that we are likely to encounter an expanding bubble within the next billion years or so. The model predicts roughly 3 grabby civilizations currently existing in the observable universe. The disturbing implication is this: if the Grabby Aliens model is correct, and if grabby civilizations expand at, say, half the speed of light, then the expansion front of the nearest grabby civilization, the edge of the sphere of space that it has modified and occupied, will reach our solar system within a geologically predictable time frame. When it does, whatever that civilization has become over billions of years of development will encounter us. And the question of whether that encounter is benign or catastrophic depends entirely on the values, capabilities, and resource calculations of an entity so different from us that we cannot currently model its decision-making in any reliable way. The Grabby Aliens model is not a dark forest. There is no universal shoot-on-sight policy. There is no predator civilization. There are simply expanding civilizations that will eventually reach us, and the encounter is coming, and whether it is welcome depends on factors we cannot currently control or assess. The transcension hypothesis. Dark implications. The transcension hypothesis, developed by futurist John Smart, proposes that civilizations do not expand outward into space but inward, into increasingly miniaturized, dense, computationally rich environments. On this view, civilizations that reach a certain technological threshold shift their focus from expanding across physical space to expanding within computational space, creating ever more complex and rich inner universes of simulated experience within increasingly compact physical substrates. The reason we do not see evidence of alien civilizations expanding across the galaxy is not that they do not exist, but that they have withdrawn into their inner worlds, invisible to our astronomical surveys. The benign version of this hypothesis simply means civilizations choose a different direction of development than we might expect. The dark version asks a more uncomfortable question. What happens when a civilization that has transcended into its inner world encounters a civilization that has not? A transcended civilization might be entirely indifferent to our existence, too engaged with the richness of its inner worlds to care about the outer universe we inhabit, or it might treat the outer universe, including us, as a potential resource for additional computational substrate. The distinction between indifference and exploitation depends on the values of the transcended civilization, and we have no way to assess those values from our current position. The dark implication of the transcension hypothesis, when combined with the Fermi Paradox, is that the universe might be full of civilizations that have effectively withdrawn from observable space while retaining the capacity to act within it. These civilizations would be undetectable by our current surveys. They would not broadcast, would not build megastructures, would not modify stellar environments at detectable scales. But they would be there, and if any external circumstance, our own expansion into space, our development of technologies that impinge on their computational substrate, our accidental or deliberate production of signals they cannot ignore, causes one of them to re-engage with the outer universe, the encounter would be between an entity, billions of years of inner development beyond us, and a civilization that has had radio technology for a century. In that encounter, the asymmetry would be total. The final silence, when the universe itself is the filter. There is one more dark possibility that sits outside the category of predatory civilizations and autonomous machines, and it is perhaps the most disturbing because it is the least personal. It is the possibility that the universe itself has a mechanism, not an intelligent one, not a designed one, but a natural physical process that terminates civilizations at or near the technological level we have reached. The candidates for such a mechanism include gamma-ray bursts, which are among the most energetic events in the observable universe, and which, if they occurred within a few thousand light-years of an inhabited planet, would irradiate the planet with sufficient energy to eliminate complex life in the illuminated hemisphere. The rate of gamma-ray bursts in the Milky Way is estimated at roughly 1 per million years. Given the 8 to 10 billion year history of the galaxy, thousands of gamma-ray bursts have occurred, and any planet within the danger zone at the time of a burst would have experienced catastrophic sterilization. Models of gamma-ray burst rates and directions suggest that Earth itself may have experienced near-extinction events from this source in the past. Supernovae represent a similar mechanism, with a smaller danger zone but a higher rate. The passage of the solar system through spiral arms of the galaxy, regions of elevated density and elevated supernova rates, may produce periodic increases in extinction risk. The solar system currently sits in a relatively quiet region between spiral arms, which may itself be a contributing factor to Earth's survival to technological civilization. These natural catastrophic mechanisms do not explain the Fermi Paradox completely. They represent probabilistic risks that should have spared some civilizations even if they eliminated others, but they contribute to the overall picture of a galaxy that is more hostile to complex technological life than intuition suggests. The synthesis of all these mechanisms, natural catastrophes, self-inflicted collapse, berserker machines, dark forest predation, dominant civilizations, and the various other filters, produces what researchers sometimes call the gauntlet model of the Fermi Paradox. The path from simple chemistry to interstellar technological civilization passes through so many independently fatal bottlenecks that almost nothing makes it through. Not because any single mechanism is universally lethal, but because the combination of all of them, applied across billions of years of cosmic history, reduces the survivors to a number approaching zero. Chapter 8. What we should actually do. The implications of the dark solutions. Here is the question that matters most, and the one that the Fermi Paradox ultimately forces on us. If there is a significant probability that one or more of the dark solutions is correct, how should that change what we do? This is not an abstract question. There are decisions being made right now by people and organizations with varying degrees of public accountability that directly engage with the dark solution problem. Decisions about whether to transmit powerful, deliberate signals toward other star systems. Decisions about the pace and direction of space development. Decisions about how to prioritize existential risk research and mitigation. Each of these decisions has different implications depending on which, if any, of the dark solutions is correct, and the range of implications is wide enough that getting the decision wrong in the wrong direction could be extremely costly. The meaty problem: should we be broadcasting? The messaging to extraterrestrial intelligence debate, METI, as distinct from SETI, the search for extraterrestrial intelligence, has been conducted in various academic and institutional forums for decades, and it has intensified significantly in the years since astronomers began seriously cataloguing exoplanets and SETI searches failed to find signals. The anti-METI position, articulated most prominently by Stephen Hawking in the final years of his life and supported by a significant number of astronomers and physicists, is essentially the dark forest argument applied as practical guidance. We should not broadcast because broadcasting announces our location, and in a universe where dark solutions may be operative, announcing our location is dangerous. The signal we have been inadvertently broadcasting for a century, our television and radio leakage, cannot be recalled. But deliberate high-powered transmissions specifically designed to be detectable at interstellar distances are different in magnitude and in intent. A beacon is different from leakage. The Prometee position argues that our passive radio leakage has already been expanding for 100 years, and any civilization within 100 light-years with sufficient sensitivity can already detect our presence. Broadcasting deliberately does not reveal a presence that is not already detectable. Additionally, any civilization advanced enough to pose a credible threat to us is almost certainly advanced enough to detect our passive emissions already, rendering METI irrelevant to the threat calculus. And silence has costs. If there are benign civilizations out there who would share knowledge or extend protection, our refusal to broadcast limits our ability to initiate contact on our terms rather than waiting for them to find us. Both positions have merit. The meta question, whether we can reliably assess the risk of broadcasting given our fundamental uncertainty about which Fermi Paradox solution is correct, is one that does not have a clean answer. What we can say is that the dark solutions, if taken seriously as more than zero probability hypotheses, should produce some degree of caution. Not necessarily absolute silence, but an awareness that the calculus of first contact is not obviously favourable, and that decisions about how, when, and with what content to deliberately broadcast should be made with deliberate care rather than enthusiasm. The current situation is that no international governance structure exists for METI decisions. Any organisation with access to a large radio telescope can transmit toward other star systems without any formal review process, institutional oversight, or assessment of whether the transmission represents a net benefit or a net risk to humanity as a whole. This is a governance gap that has no obvious mechanism for correction in the current international environment, and it is a gap that the dark solution suggests should be taken seriously. The case for becoming interplanetary. Now, regardless of which dark solution is correct, all of them share a common implication for the question of human expansion into space. If the Great Filter is ahead of us, if technological civilizations tend to destroy themselves or be destroyed before reaching multiplanetary status, then becoming genuinely multiplanetary and eventually interstellar is the most important thing our civilization could do to improve its long-term survival prospects. A species confined to a single planet is vulnerable to every form of extinction: asteroid impact, supervolcanic eruption, climate catastrophe, pandemic, nuclear war, gamma-ray burst, and every form of civilizational collapse. A species distributed across multiple planets and eventually multiple star systems is robust against any of these threats in any particular location. The development of genuine multiplanetary civilization is the most effective known response to the filter ahead problem, because it converts a single point of failure civilization into a distributed one. This is not a new argument. Carl Sagan made it, Stephen Hawking made it, Elon Musk has made it repeatedly as a justification for space development. What the dark solutions add to the argument is urgency. If the filter ahead is something that typically terminates civilizations within a specific range of technological development, within the first century of nuclear capability, or the first century of genetic engineering, or the first few decades of artificial intelligence, then the window for establishing multiplanetary civilization before encountering the filter may be short. We are currently, by most estimates, within decades of having the technical capability to establish permanent human presence on Mars. Whether we do so within the relevant time frame, before encountering whatever filter may be ahead, is a function of political will, resource allocation, and the absence of the very catastrophes the multiplanetary capability is meant to protect against. The circularity of this is frustrating. The filter, if it is real, might prevent us from developing the technology that would protect against the filter. The race between developing the capability and encountering the threat that makes the capability necessary is not obviously going in a favourable direction. Listening before speaking, the SETI imperative one specific and relatively low-cost implication of the dark solutions is that SETI, the search for extraterrestrial intelligence should be prioritized as one of the most important scientific programs humanity has ever undertaken. Not because finding a signal would be good news, finding a signal might be the worst news we have ever received, depending on its content. But because the information content of a detected signal, or the information content of a carefully characterized absence of signals, is enormously valuable for calibrating our own behavior. If SETI detects a signal that is clearly of artificial origin, but that contains no obvious threat characteristics, no instructions, no signals that activate some response in our technology, just a clear carrier wave indicating the existence of another intelligence, the implications are profound. It would confirm that we're not alone, that the Great Filter is not in early biological evolution, and that at least one other civilization has survived to the technological stage. This would simultaneously be the most exciting discovery in human history, and a reason for extreme caution about how we respond. If SETI detects no signals despite searching with significantly improved technology, if the next generation of radio telescopes with their orders of magnitude greater sensitivity still finds nothing, the absence itself is informative. It narrows the range of Fermi Paradox solutions consistent with the data. A truly comprehensive SETI null result would push the probability distribution away from the they are there but not broadcasting explanations, and toward either the genuine rarity of intelligence or the genuine predation of detectable civilizations. In either case, signal or improved null result, the information is worth having. The cost of SETI is small compared to the value of the information it could provide. The currently funded SETI programs represent a few tens of millions of dollars per year, less than the budget of a medium-sized scientific mission. For a program that is attempting to answer what may be the most consequential question in science, the resource allocation is absurdly small. The dark solutions provide a specific argument for increasing it. If any of them is correct, knowing sooner rather than later is better than not knowing at all. The paradox as a mirror. There is a final and perhaps most important implication of the dark solutions to the Fermi Paradox that goes beyond specific policy recommendations about METI and SETI and space development. It is the implication that the dark solutions hold up a mirror to humanity and to the trajectory of our own civilization. The dark forest civilization, the one that has learned to shoot on sight, that has abandoned cooperation in favor of preemptive destruction, did not start that way. It started as something like us, curious, expansive, looking at the sky and wondering what was out there. It traveled a path, through technological development, through existential crises, through whatever combination of resource pressure and survival calculus and civilizational trauma that ended in the dark forest philosophy. We do not know what that path looks like from the inside. We do not know whether it was inevitable or whether the civilization had choices at key junctures that it failed to take. The Berserker civilization, the one that built the machines, also started as something like us. It solved its Fermi paradox at some point in its history, and decided that the solution warranted the construction of a galactic police force of autonomous killers. Was that decision rational? Was it moral? Was it the decision of a civilization under threat, reacting to evidence of hostile intent from its neighbours? Or was it the decision of a civilization that could have made a different choice and chose not to? We are at the beginning of our own answer to the Fermi paradox. We have detected no other intelligence. We are developing in real time the technologies that could make us either a dark forest civilization or a berserker builder or a transcended inner world civilization or something we do not yet have a name for. The dark solutions to the Fermi paradox are not just explanations for why the sky is silent. They are possible futures. They are the trajectories that our own civilization might follow if we make specific choices about how to handle the existential risks we face, how to develop the technologies we are building, and how to relate to any intelligence we eventually find. The silence of the sky might be the accumulated consequence of civilizations that face the same choices we face and chose poorly. That is the darkest implication of all. Not that something external will destroy us, but that the path from here to there, from curious primate species to whatever we become in a million years, passes through choices we're making right now, and that the wrong choices lead to the silence. Shaktas, conclusion. We began this video with the silence of the sky and the question that silence poses. Where is everybody? The comfortable answers. Life is rare, intelligence is rarer. They haven't had time. They are communicating on channels we haven't searched. fail in specific and quantifiable ways when you push on them. The temporal version of the paradox, the version that asks not just, where is everyone now, but where is the accumulated evidence of everyone who has ever existed across 8 billion years of galactic history, makes the comfortable answers harder to sustain with each new sky survey that comes back clean, each new exoplanet characterized without industrial chemistry, each new infrared survey that finds no Dyson spheres. The dark solutions do not fail in the same way. A dark forest universe would look exactly like the universe we observe. A universe patrolled by berserker machines would look exactly like the universe we observe. A universe dominated by a single ancient civilization that eliminates competitors early would look exactly like the universe we observe. The dark solutions are consistent with the data in a way that the comfortable answers are increasingly not. This does not mean the dark solutions are correct. Consistency with observations is a necessary but not sufficient condition for a hypothesis to be true. All of the dark solutions require specific assumptions about the universality of survival drives, about the resource constraints facing interstellar civilizations, about the decisions made by beings so different from us that our models of their decision-making are essentially guesses that may themselves be wrong. But the epistemological situation is clear. The comfortable answers require specific assumptions that are increasingly difficult to defend as astronomical data continues to accumulate. The dark answers require specific assumptions that are difficult to verify, but difficult to rule out. The probability distribution over all possible explanations for the Fermi Paradox has, in recent years, shifted toward darkness, not dramatically, not definitively, but measurably. And there is a specific reason why that shift in probability distribution matters beyond its abstract philosophical interest. It matters because we are currently at the stage of development where, according to the dark solutions, civilizations become detectable and therefore potentially vulnerable. We have been broadcasting for 100 years. Our radio bubble has reached thousands of star systems. We are developing technologies that might trigger whatever filter or threat is ahead of us, if any is. We are making decisions about METI, about space development, about artificial intelligence, about the management of existential risk, that will determine what our civilization looks like in 100, 1,000, 1,000,000 years. If the dark solutions are partially or fully correct, these decisions are being made in a context that most people making them do not understand. The context is a galaxy that may not be a nurturing environment for young civilizations. A galaxy where the default outcome for a civilization that does what we are currently doing, broadcasting its presence, developing powerful technologies without adequate safety frameworks, failing to establish genuine multiplanetary redundancy, might be the same as the default outcome for most civilizations that reached our stage before us. The silence of the sky is a message. We do not know for certain what it says, but the most honest reading of the available evidence suggests that the message is not "you are alone and the universe is safe." It is something more ambiguous, more unsettling, and more in need of a thoughtful response. The sky is dark, the forest is quiet, and somewhere in the dark and the quiet there may be something watching us decide what to do next. Thanks for watching.